Hello, this lecture will cover page 34 of my lecture notes. Please print that page out and have it in front of you as I present this lecture on resistive circuits, chapter 2E, problem solving series parallel circuits. If you take a look here on page number 34 of your lecture notes, it talks about some example problems, 219, 220, 222, and 223 in your book. You definitely want to look those over before you try to tackle the homework. Let's take a look at 219 here. We're just going to take a look at one of these and just to give you an idea of what you're going to expect. But here's a circuit, and they want you to find the current through this load resistor IL out here. This RL 12K ohm load resistor. They want to find the current IL through it. What they do is they simplify that circuit, and since these current sources are all in parallel, you can algebraically just add them up and you get 1 milliamp flowing down. That eliminates these three with 1. And then you want to preserve the element, in this case that the current flows through that you're trying to find. You put the 12K out there, and then you put the 18K in parallel with the 9K in parallel with the 12K, and there's the equation for that, and it's equivalent to 4K, and you get your 4K. And then look what they do here to find IL. Okay? Look what they do to find IL. The direction of IL flows down, but you know that can't be right because the 1 milliamp current source is flowing down also. So the currents in this circuit have to come down over up through the 4K and up through the 12K. That's going to make IL minus. But they take care of it over here with that negative sign. But what are they doing here? It's just the current divider rule. The IL here is equal to the total current, they put it last year, the total current coming into that node times the opposite resistor, which is the 4K, divided by the sum of the resistances. And you get a negative 0.25 milliamps answer here. I want you to notice something, that whenever you have resistors in parallel, a quick check is that when you come up with an equivalent resistance, it's always less than the smallest resistor. Think about that. Whenever you have resistors in parallel, the equivalent resistance is always going to be smaller than the smallest resistance. That's just a real quick check to make sure you're at least in the ballpark there. You also want to take a look at examples 220, 222, and 223. They used the current divider, the Kirchhoff's current law, Kirchhoff's voltage law. They used the current divider rule, and they used the voltage divider rule. We're going to look at learning assessments, and we're going to go through problems 217, 218, 220, and 221, one at a time. It's in the textbook. You're going to have to work these out on your own, so what I'd recommend is here, the best way to do this, it takes a little time, but grab a scrap sheet of paper here, and a pencil and a calculator, and here's your circuit for 217, learning assessment. And what they want you to find here is V out. They want you to find the output voltage. They just extend these terminals here, and the output voltage is just the voltage across this 20K ohm resistor. So I want you to try to find that. Stop the video and try to find that using the techniques, the tools that you have in your toolbox to do that. And here's the solution. Okay. One method is to find the voltage at node A. I labeled that node A. And then use the voltage divider rule. So if you take a look, what I've done here is I've taken the 40 and the 20, added them up and got 60. Made one resistor out of these two resistors up here. And that puts the 60K in parallel with the 30K. I got equivalent resistance there. And you could see it's just 18 over 9. Think about that. If you just take the 3 times the 6 over the 9, you know it has to be 20. You know, product over the sum. 18 over 9 is 2. That has to be 20K. You can use a calculator, no problem. You get 20K. Then you add it to the 20K. Well, you know, we're not interested in the total current here. All you want to do is use the voltage divider rule now. The voltage divider rule said the voltage of point A with respect to this being ground down here is 12 times the 20 divided by the sum of the two. That's 6 volts. So now you have 6 volts at this point, which is really this point. You go back to the original circuit, and VA right there is 6 volts. And you use the voltage divider rule again. From this point, looking in this direction. If that voltage there, you can just forget about this here. If that voltage right there is 6 volts, the voltage out here across the output, using the voltage divider rule, is VA times 20 divided by the sum of the two, 60. It's 2 volts. There's your answer. Another method would be to find RT and then find the total current. Then use the current divider rule to find the current through RL, the 20k ohm resistor. Once you know the current, use Ohm's law to find V out. Look at the circuit. You might have worked it this way. Some students work it this way. You find the total equivalent resistance of the circuit. Then you find the total current, 0.3 milliamps. Then use the current divider rule. That current divider rule is going to give you what I labeled I1 up here. It's the current coming out this way. That's 0.1 milliamps. And then using Ohm's law, if you have 0.1 milliamps coming out this direction, well, it can't go out here. I mean, this current's zero. It's an open circuit. This current is zero flowing. So all the current flowing through the 40k ohm resistor has to come down through the 20k ohm resistor. And that's what we're interested in. So you use the Ohm's law here, you get 2 volts. You get 2 volts either way. The next problem I want to look at is 218. There's problem 218. I'd like you to copy it down, piece of paper, turn off the video, see if you can find VS. VS is the source now. They're giving you a current over here, and they want you to work backwards and find this source. Once you do that, you have to try it on your own, and you have to hit that wall. Once you hit that wall, then you can take a look at my solution and you learn something. The first thing you want to do is find VA. I just labeled this point VA with respect to ground. This is 0 volts down here, so what's VA going to be? Well, you know 2 of the 3 things right here in Ohm's law. You know the resistance and you know the current, so you know the voltage across it. Always look for 2 out of 3 things. 2 of the 3 parameters in Ohm's law. That'll really help you out. In this case, VA is 6 volts. That's 6 volts. The second thing you do is find the total current. Well, if this is 6 volts right here, okay, well, let's find I2 first of all. If you want to find I2, you're finding IT, but to find IT, to find this total current here, you know the voltage of point A, so these 2 resistors are in parallel, so you should be able to find I2 now. You know, if you knew the voltage across the 60k is the same voltage across the 120k. I make that calculation, I get 50 microamps. And then using Kirchhoff's current law at this node, now you can get the total current of 0.15 milliamps. Just do Kirchhoff's current law at this node. The current's entering, half the current's leaving. Once you find that total current, you can find the voltage across that 20k ohm resistor, which is 3 volts. And then I just go around this loop here using Kirchhoff's voltage law. Some of this you can do in your head. Some students say, well, if the current is flowing this way, in this direction, it's plus to minus. Don't forget the passive sign convention. And we know the voltage across the 20k is 3 volts. So if you're at ground here, and you come up, and at VA, we already said at VA, that voltage was 6 volts, and then you come up another 3 volts, which we calculated here, that leaves 9 volts for here. The source has to be 9 volts. But what are we really doing there? We're really just going around this loop right here using that very simple Kirchhoff's voltage law around the left loop. There's that equation. If you put this on an exam and you make a simple mistake from here to here, I can give you credit. If you're chicken scratching and you're not writing your equations like you see here, I can't give you partial credit, and your grade's going to suffer. VS is 9 volts. The second way in this problem right here is you can find RT and then use Kirchhoff's voltage law. Okay, you can find the total resistance of that circuit, and you could work with that. But what I would recommend, I wouldn't recommend even looking at that. That's going to lead you back to this same solution here, to tell you the truth. You know what? There's not a second way to do that. I mean, the only way to do this problem is look for 2 out of 3, and you know it here. And you find VA. The answer is 9 volts. The next problem I want you to try on your own is this problem, E220. There's the circuit. And they want you to find V1. They want you to find this voltage V1 right here, and they give you the polarity, plus to minus. Well, this is a parallel circuit. At least these 2 current sources are in parallel. So I combined them algebraically. That makes 10 milliamps flowing up. And I labeled IT. I labeled I1 and I2, just so I can write equations so you can see what I'm doing here. This is a current source. You don't use voltage divider rules on current sources. On current sources, you use current divider rule. On voltage sources, you use the voltage divider rule. Okay? Well, I said by Kirchhoff's current law. Okay? That's not true. That's not by Kirchhoff's current law. That's by the current divider rule. By the current divider rule, what you can say here is I1 is equal to the total current coming into the node times the opposite resistance, which is 6 times 10 to the third, divided by the sum of all the resistances. Don't just pick 2 of these. It's the sum of all the resistances. 15 times 10 to the third. It's equal to 4 milliamps. Once you know 4 milliamps is flowing through this circuit here, it's flowing through this part of the circuit, the 3K and the 6K, Ohm's law tells you that voltage V1 is 12 volts. Try to stay away from writing 6K in the equations. Or if you have current, try to stay away from writing 2 milliamps. Try to stay away from doing stuff like this. The voltage is equal to, let's say, 2K times 3 milliamps. You know, you end up losing these notations, and you'll get your magnitudes off. What I'd like you to do, and discipline yourself to do this. Write that as 2 times 10 to the third. That's the resistance, and the current is 3 times 10 to the minus 3. That's milliamps. And then when you work that out, that's just simply 6 volts. Try to put the magnitude, the exponents in like that, rather than the abbreviations, K ohms. Don't try to put units and prefixes in equations. And then finally, 221. Here's problem 221. There's the original circuit. They want you to find the current I.O. through that 3K resistor. Well, right away you can see that the current's coming down here, and they're labeling this current coming down, so this current has to be negative. The currents in this circuit come down and come up and come up and come up. They join together here and they come together at that node and come back to 9 milliamps. It's like water flow. Think of that as like water flow. So what you learn here right off the bat, that the answer has to be negative. The answer is going to have to be negative because that current, the way they have it shown in the wrong direction. So first, find I1. Now the first thing I do is I label I1s. I labeled I1 here. You're going to see I didn't need to label the current here or the current here because I don't need that in any of the equations. But there's their I0. I put an I1 here and I put it in the correct direction. That direction is up. And then I basically redrew the circuit. No, I'm losing the identity of I0. I realize that, but I have to find I1 first. So I'm going to lose the identity temporarily. Product over the sum of 3K and 6K. If you think about it, it's 3 times 6, 18 divided by 9. So it has to be 2, but where do you place the decimal point? What's 2K? So the equivalent resistance here is 2K. And all I'm doing is I'm using the, at this case right here, I'm using the current divider rule. It's very popular. You have to get that current divider rule down. It's the total current coming in, okay, to this node here, times the opposite resistance, 12, because I want to find the current here. So it's the opposite resistance, 12, divided by the sum of the resistances, which is 18. It's 6 milliamps. The current I want is 6 milliamps. Now we can find the voltage at point A. This point up here, we can find the voltage there, because the equivalent resistance here is 2K, so that voltage is minus 12 volts. There's minus 12 volts right there, with respect to this being ground. If you're at 0 volts here, by the time you get up there, you're at minus 12. Or minus 12. How do I know that? Well, you know that when current flows, it's plus to minus. It's plus to minus. So if you're at 0 here and you have a drop plus to minus, this is the equivalent. It has to be a negative with respect to that. And it is. It's minus 12 volts. Looking back at the original circuit then, with VA being a minus 12 volts, use Ohm's law. You have a minus 12 volts there, and you have 3K. That current is minus 4 milliamps. That's the solution to that problem. We could just continue to work problems, and that's what this course is all about. And I'm pretty good at working these problems. I mean, I might make a silly mistake now and then, and you have to try to minimize that. And as I work these solutions, you might even find that I had a simple mistake there, and you'll point it out to me when you see me in lab. But for the most part, it's a problem-based class, which means you have to work lots of problems. And those of you that can put the time in and get these techniques down, you'll be rewarded, because the exams will be a lot easier for you. If you can't put the time in and you don't work these problems, you're going to find it difficult. You're going to find it very difficult. So I'm working as many as I can to be reasonable here. And I'd like you to continue on with the homework. That concludes this problem-solving lecture.